We discuss Lenz law in this lecture. Faraday's law states that the induced EMF has opposite sign compared to the rate of change of flux. The physical interpretation of this statement is Lenz law. Lenz law states the following. The induced current travels in the direction that will create a magnetic field with flux opposing the change in original magnetic flux. Lenz law is consistent with energy conservation.
We're going to use Lenz's law to find
Let's
the direction of
understand
the
Lenz's
induced
law
current
through
for
a
the coil
practice
sitting in a
example.
magnetic field as shown in this diagram. The magnetic field points straight up and is increasing in magnitude. Because of this, the net upward flux through the area of the coil is also increasing. The coil responds to this by producing its own magnetic field, which is pointed down, by virtue of the fact that a current is induced in the clockwise direction. So the induced magnetic field must oppose the change in flux, and the key word here is the change in flux, not the initial direction of the flux, but how it's changing. So if I look at these four cases, in fact, this case that we just looked at corresponds to D. And again, magnetic field lines flow into the south pole of a magnet, and if I bring that magnet closer to the loop, I get more field lines flowing upward through the surface of the loop here. And the loop responds by producing its own magnetic field that's going to be pointed down. And hence that sets the direction of current flow.
Let's watch another demonstration.
Now, for a more dramatic demonstration of Faraday's law and the effects of Lenz's law. When the current is switched on, a magnetic field is produced that induces a current to flow in the aluminium ring. Like all currents, this induced current will produce a magnetic field of its own. Now, Lenz's law states that the direction of any magnetic induction effect is such as to oppose the change producing it. So the direction of this induced magnetic field must be in opposition to that from the coil. The ring experiences a repulsive force and is launched into the air. We can easily show that the force launching the ring into the air comes from an induced current flowing in the aluminium ring. This time, there is a gap in the ring. It isn't a complete circuit, and so no current flows. Now, what would you expect to happen if we repeat the experiment with the original ring, but this time we cool the ring first? You should recall that when we cool a conductor, its resistance decreases. This means that the induced current that flows in the ring is much larger, and so the repulsive force experienced by the ring is also much larger. We've seen what happens when
This demonstration is also due to Lenz's law. So we have two different tubes. One cup, one is a metal, one is glass. As we can see, the magnet drops through the metal tube much slower because the induced current in the metal tube would oppose the motion of the magnets.